Okay, in this homework problem, we're going to look at the ideal ranking cycle with superheat and do a little sketch here if I can of start with pen. So we've got a turbine, goes into a condenser, goes into a pump, into a steam generator, and back into the turbine. So turbine, condenser, pump, and steam generator. State 1, state 2, state 3, and state 4. And some simple relationships. Delta S equals 0. Delta P equals 0. Delta S equals 0 for the pump. Delta P equals 0 for heat exchanger. So for the steam generator and the condenser, delta P equals 0, no pressure drop across those devices. There is a pressure drop across the turbine and a pressure rise across the pump, and but no entropy change in those two devices. So on a pressure entropy diagram, it would be a square. The turbine, there's pressure drop, constant entropy, and then a reduction in entropy in the condenser until we're in a saturated liquid. I'm not going to draw the saturation curve here. And we just have a rectangle, square, depending on the units. So state 1, state 2, pressure drop. State 3, constant entropy to state 4. And so the pressure drop from 1 to 2 has to equal the pressure rise from 3 to 4, obviously, if those are two horizontal lines. So there's only two pressures, P low and P high. On a TS diagram, it looks a little different. So on the saturation curve this time, here's the high pressure line, here's the low pressure line. So this is P high, P low. Start here at state 1, come down to state 2, state 3, straight up here to state 4. Now, state 2, I have here state 1 up here. State 2, which I have, that's state 2. That state doesn't have to be saturated. It could be saturated liquid vapor mixture. It could even be superheated. So it just depends on the problem. All right, so now I have some context of constant pressure, constant entropy. I know P1 is 80 bar and T1 is 640. So from those two values, I can go to the superheat tables and find H1, and I can also find S1. The reason I want S1 is because if S1 is there, then S2 is the same thing. So S2 is at the same place on the axis, so S2 equals S1. So that I'm heading to what I need for state 2. Also, I was given P2, which has the same pressure as state 3. So P2 is right there. P2 and P3 are the same. S1 and S2 are the same. All right, so I would go to the, I think I may have this downloaded, the thermal booklet. And I'm going to scroll down quite a ways to superheat tables. I guess I should have looked, but maybe 10 bar, some temperature. So I find make sure I'm in the tables for water, A4, and find the table that has the pressure that I'm at and the temperature that I'm at. So let's take a look. We're at 80 bar and 640. So higher, 80 bar, 640 is here in the table, and we have a little hard to see which column's which, but top here, enthalpy in kilojoule per kilogram, and entropy is the last one. So at 80 bar, 640 is 3738.3 and 7.1283. So 3738.3. kilojoule per kilogram. and S is 1.7 something. 80 bar, 640, no, 7.1283. 7.1283 kilojoule per kilogram Kelvin. Right, so now maybe think a little bit ahead of where we're going, but for the turbine, of course, dE CV dt, this is my system boundary. So I'm just looking at turbine 1, or the only turbine. If I apply the first law to that, so my control volume is everything inside the turbine. Heat transfer across that boundary minus W. I'm going to assume it's, well, I'll write it out. I have one inlet and one exit, so I'm going to write this as plus m dot times each. Let's use the states that are listed there. The inlet is 1 minus H2, and then plus change in kinetic plus change in potential. And I'm going to say there's no change in kinetic or potential. Anyway, I don't have any information about the diameters of the pipes or the elevation. And it's adiabatic. That's typical assumption if we don't have other information. Generally don't want heat transfer in a turbine. And we're going to say it's steady state. Steady state because this isn't some startup condition. There's nothing about time, like the pressure is a function of time or the temperature one is changing with time. So we'll bring work to the other side of the equation and we'll get W dot for the turbine equals m dot through the turbine times H1 minus H2. And if we apply the first law to the condenser, we would get Q for the condenser equals m dot, and this time we'll have exit minus inlet because we're going to leave the Q on the right side of the equation, move the other terms over, so we'd have H3 minus H2. This would give us a negative value, which it should be. It's Q out. The work for the pump, again, if we use the first law, we'll get almost the exact same equation. I put actually H inlet minus H exit. Probably should have put 2 in there, so let me try and use this. Kind of mixing 1 and 2 and inlet and exit. M dot times, I've got inlet minus exit, so H3 minus H4. Of course, that again will be a negative number. And then finally, the Q for the steam generator is m dot, and I have H exit minus inlet, H1 minus H4. And that will be a positive number because it's Q in. So this will be positive, negative, negative. Cross that out. Negative. Keep wanting to write Q's. Negative and positive. So then finally, the efficiency is going to be the desired output, which is the network. And I'm putting a plus pump because the pump is going to be negative, divided by the Q in, which is Q for the steam generator. And I don't need to put the condenser heat transfer because the condenser, there's no cost for that. So that's, we can dump energy to the environment free of charge. So there's my efficiency, of course. To find all those terms, I need all the H's. So that would be the next step. So I found H1 already, and I'm going to try and erase this and then calculate all the H's. So I guess keep this in mind. Ultimately, then this is going to be, the efficiency is going to equal, of course, the m dots will cancel. Every term has the same m dot. So H1 minus H2 plus H3 minus H4. I can't write on the edge there. So that's H4, a little hard to write there, over H1 minus H4. And this term right here is H4. And so now we find H1 through H4. All right, I made some room so we can find the other enthalpies. So for state 2, I know the pressure. Pressure at state 2 is 0.08 bar. And S2 is 7.1283. And from those things, I want to find H2. Now, I'm probably going to have to do some interpolation. So at 0.08 bar, 7.1283, let's see if it's superheated. So I start going down in pressure and I find 0.15, 0.1, 0.07. So before I start interpolating, let's go to the saturation tables and see if we can find 0.08 bar, and it's this third row. And at 0.08 is equal to 7.1283, and if we look at the pressure of 0.08 bar, we see that 7.1283 is between 0.5926 and 8.2287. So we know it's a saturated liquid vapor mixture, and so we need to find the quality at state 2. Quality at state 2 is defined as S minus SF over SG minus SF. And we know S at state 2, it is 7.1283 minus 0.5926 divided by SG, which is 8.2287 minus 0.5926, and do the math and I get the quality. Once I have the quality, I can find H, because H is defined the same way. H at state 2 minus HF over HG minus HF. And so I get that H2 minus HF, in this case at 0.08. HF is 177.88. Sorry, 173.88. If I can erase this. Let's see. Oops. Go back to the pen. Divided by an HG minus HF is also called HFG, so I can use that if I want. I can do 2577 minus 173.88, or that value would be 2403.1. And now I know the quality from this one, so I use that quality, put that in there, and solve for H2. So again, this is S2 and H2. And if I do the math, this is approximately 0.856, more exactly 0.855895, and I put that value in here, 0.856, and solve for H2. And if I do that, I end up with the answer for quality here is 0.856 or 85.59%. And then the enthalpy 2 at the turbine exit is 2230.7. Right, then determine the specific enthalpy at the condenser exit. At the condenser exit, so here I have 2230. Right, then H3, I know at state 3, the quality is also known, and so I know the pressure, and with these two values then, so I'm looking for H3, so I can get that from the quality and the pressure, and I get that H3 equals quality is 0, saturated liquid at the pump inlet, so HF at P3. So I go to the saturation tables, go back to, I guess I can do it here. Pressure is 0.08, and we've already looked that value up. It's one we've been working with. It's the 173.88, so that's HF at 0.08 bar. And right, and then finally I need H4 at state 4. We have the same entropy as state 3 and same pressure as state 1. So at state 4, P4 equals 80 bar. And S4 equals S3, which means that T4 has to equal T3 from our saturated liquid approximation, because S4 is only a function of T4, and S3, which we know is equal to S4, is only a function of T3 for our saturated liquid approximation. That means that T4 must equal T3. It's the same function. So if it's only a function of one parameter, same function, then that means it must be the same temperature. So we're going to use the saturated liquid approximation, and I'm kind of running out of room here, so I'm going to scroll down a little bit. And so H4, we're going to use the saturated liquid approximation. It's going to be HF at the temperature that we're at, which is T4. Now it happens to be T3 too, but I'm going to write T4, but T4 equals T3 plus the saturated liquid specific volume, again evaluated at T4, times P4 minus Psat evaluated at T4. And I'd rather you use the temperature at state 4 than being tempted to put in T3 there, because maybe we don't know what T3 is. Maybe it's just I tell you the temperature and the pressure of a subcooled liquid, and I want you to find the enthalpy. It doesn't really have to be related to a pump. So better to make note here that T4 equals T3, and then just use T4 in this equation. So I would have HF at T4. How would I find T4? Well, it would be the same temperature as T3, so let's find it. So what is the temperature of the condenser? And if I go here, I find that it is 41.51 right there at 0.08 bar. So go back here. So T4 equals T3, which equals 41.51 degrees C. So this is going to be at 41.51 degrees C. And that's going to be all these values I'm going to find at my T4. Now, rather than going to the tables that have temperature, go ahead and use table this table. And so these are the values at 41.51. And so you would use HF, which is 173.88, but we're thinking of it now as at 41.51 degrees, plus VF, which is 1.0084 times 10 to the minus 3, because it's been multiplied by 1,000, times our pressure, sorry, not 1.0084 at 41.5, this one, this value right here. And then times the pressure, which happens to be 80 bar, minus Psat, which is 0.08. Right, so let's go back and write those if I can remember some of those values. So this will be, HF is 173.88 plus VF is 1.0 something. Let's take a look again. 1.0084 times 10 to the minus 3. 1.0084 times 10 to the minus 3 times our pressure. I'm going to put the pressure in kPa so our units work out. So I'm going to have 8,000 kPa. Minus our pressure in kPa, which is 8, which is the saturation pressure at 41.51. So I take 173.88 plus 1.0084, that's an 8, it's like a 9, times 10 to the minus 3 times 7,992. And if I do that, I will get the enthalpy at the pump exit, and I'll get 181.94. It's not a whole lot different than this one, but it accounts for the pump work. So 181.94. So all that, H4 equals 181. All right, now I have all the H's. I find the power produced by the turbine. I already have those equations. I erased them. I just do m dot times that enthalpy difference, the power for the pump, m dot times the temperature difference. Here I want it as a positive answer, so if I add them together, I'm going to have to do one minus the other if I put a positive value here, but the net value would be the pump work minus, the turbine work minus the pump work would be the net. Or if we express this as a negative value, then we'd add the two together. And then the heat transfer supplied to the boiler. I have all the H's, so H1 and H4 times m dot. H1 minus H4 times m dot is my heat transfer supplied to the boiler. Look at this. I take the net work over Qn, and I'll get 42.165. Your problem is much the same, just different values, looking up different values in the tables, same procedure. But really do try and think through how to do this problem. Make sure you understand each step. Try and do this without watching the video while you're doing it. If you can remember all the steps, you've probably learned it.